All right, what I'll do is I will simply talk to you about the test I have in front of me, and any notes that you take can go on your review sheet. I will allow that. That would be free information, and anything I say here can be put on your review sheet. That's not a problem. So let's begin, and I'll just talk. Okay, so the first thing that you're going to see when you see your final exam is going to be questions about work, energy, and simple machines. Don't forget what power is. Power is the amount of work you do per second. So let's say that work is constant. The faster that that work is accomplished, the greater the power. Power equals work divided by time. Now, if you understand that work is force times distance, and there's no force involved, then it doesn't matter how long you're doing whatever it is you're doing. There's no force times distance because force is zero. So if a car is moving along a highway at a constant velocity means there's no net force. So if there's no net force, that means that you have no work being done. I know it's a little weird, it's a little counterintuitive, but in order to have work, you need to have force and distance as a product. Okay. Now, you have elastic and inelastic collisions. So think of it like this as a spectrum. On the right side, you have elastic or completely elastic. But let's say elastic means completely elastic. And then on the left side, you have completely inelastic or simply inelastic. But let's, for the point of this test, say that 100% efficient, no loss of energy is simply called elastic. When something mud against a wall, where there's no bouncing, nothing, we'll call that completely inelastic. So we have elastic, we have partially elastic, we have partially inelastic, and we have inelastic. So just keep those in mind as we go through this. Okay. When I have the energy of motion is kinetic energy. So when I have something moving, it's kinetic. So when you think of the words kinetic energy, that's energy of motion. When you think of the words potential energy, like gravitational potential energy, think of holding a pencil above a desk. That's a certain height above the desk. If I let that pencil go, it will accelerate due to gravity. So mgh. So the potential energy is going to be mass times gravity times the height. That's gravitational potential energy. Look up the units for a spring constant. That's always good. I'm going to start and stop this as I want to read over things as I progress. So just remember, the power is force times distance divided by time, or simply work over time. Let me take a quick break. There's also some great thinking problems here. I'll give you an example of one without giving away the answer. Non-mechanical energy, for instance, something like friction. And then you have mechanical energy, which can be conserved, but isn't always conserved. As you know, mechanical energy can be lost due to frictional forces. So a non-mechanical form of energy, friction, you have mechanical energy, and comparing the two. There's going to be a particular example of that. And what else? So let's talk about momentum. Momentum equals mass times velocity. Okay, easy. But that's not particularly usable, but it's certainly a definition and a starting point. The more important definition is change in momentum, which is change in momentum equals mass times change in velocity. Why is that significant? Because I really don't have a good understanding of the momentum I possess. If I'm in a car traveling at a constant velocity and the car has a particular mass, including its occupants, and you're just traveling on the highway, you don't really realize how much momentum the car and its occupants possess until there's a change in momentum or a change in velocity. You crash into a wall. Then you will understand more fully how much momentum you had. So when you talk about a change in momentum, a delta P, that's going to equal the force times the change in time. So the faster the change in time, the more quickly the time is, the greater the force. Yes? The longer the time span, in other words, if you're braking over a long period of time, let's say 30 seconds, then the car will slow down and you'll be safe. But if the car runs into a brick wall and the stopping time is 0.0031 seconds, then the force goes sky high. And you have various things in your car that will increase the time in which you're slowing down. For instance, anti-lock brakes, airbags, seat belts, padded dash, crumple zones, which is the front half of the car. It will crumple. It won't like stay solid and then you'll bounce. Also, don't forget, when you bounce, you're doubling the change in momentum. Look that up. It's very important. Let's take another quick break. Now, continuing our talk about momentum, remember that momentum is always conserved and it goes somewhere. Again, the moose standing on the tracks. The moose weighs a lot, weighs 1,000 kilograms, and so maybe 500 kilograms. So the moose gets hit by the train. The moose lives, of course. The moose does not die, but the train and the moose continue traveling along. The train will slow because the mass increased. So it's the mass of the train times the velocity of the train plus the mass of the moose separately. That's before the collision. And then after the collision, it's the mass of the train and moose together times the velocity. So remember, it's mv. They're indirectly proportionate. So as the mass becomes greater, the velocity will slow a little bit because the momentum is conserved. Now, don't forget, you have 4 things. It's going to be like 7 questions. You're going to have elastic. You're going to have nearly elastic. So you think elastic meaning perfectly, I drop the ball and it goes right to my hands. Perfect. Inelastic means like I drop a pencil on the table and the pencil bounces. Okay, but it's certainly not bouncing high enough. Or a ball dropping out of my hand and it bounces. It doesn't really reach my hand. So that's inelastic. And then you have perfectly inelastic, which is like mud against the wall. That's just what we're doing. Okay? So when you have something collides, is deformation, did something deform in the collision? If you lose some kinetic energy, like, for instance, billiard balls colliding. That's very elastic. So think of billiard balls, think of clay, think of dropping a pencil, think of these sorts of things. Okay, let's now talk about fluids, and then we'll take another break. Okay, a fluid is anything that flows. So any gas or liquid is a fluid. Okay, what else about fluids? Look at your equations for fluid. How do you measure the pressure of a fluid? What do you need in order to measure the pressure of a fluid? Remember how pressure can be calculated. It can be force over unit area. So it would be force divided by the area of the base, let's say length times width, okay, the weight of the object. So a book on a table could be the weight of that book divided by the area that the book outlines on the table. There are other ways of measuring the pressure of a fluid based on the height of the column of liquid or the height of the column of fluid. Let's just take a quick break so I can read some of these problems. Okay, let's continue with this. Don't forget, we're talking about pressure. Don't forget, in a column of fluid, don't forget that pressure is dependent upon the height of the fluid, or the depth, the gravity, acceleration due to gravity, and the density of the fluid. What is the nature of the fluid? What is it actually made out of? Okay, is it fresh water, salt water? Is it some kind of goo? That sort of thing. So it's going to be the fluid density, the depth, and the acceleration due to gravity. Don't forget Bernoulli's principle. If I have like a hose, and I put the hose on inside the house, but I turn off the spigot so it's not flowing, the pressure that the water is exerting on the hose is perpendicular to the hose, so I can't like squeeze the hose. But as that water flows, as the velocity of the water flows, the perpendicular pressure to the hose becomes less. Don't forget about Bernoulli's principle. Another principle is Pascal's principle. If I apply a pressure to a fluid, that pressure is distributed throughout that fluid equally and undiminished. And then there's Archimedes Principle, and that is essentially that the buoyant force is equal to the weight of the volume of fluid an object displaces when immersed in the fluid. Don't forget buoyant force. Let's see. If I have a kilogram of gold, very high density, and a kilogram of aluminum, which one is going to exert on the water a greater buoyant force? The kilogram of gold or the kilogram of aluminum? If I have 1 liter of gold versus 1 liter of aluminum, which is going to exert a greater buoyant force? The aluminum or the gold? These sorts of things. So don't forget about turbulence, about water flow, etc. Let's see. What else? If I blow on top of a piece of paper, what causes the lift? What causes lift Why does the paper lift? Go back to the definition of Bernoulli's principle. Okay, what else? All right, let's take another break, and then we'll get into some thermodynamics. All right, let's talk about chapter 21, temperature and heat. So, right, thermal equilibrium, thermal expansion, Celsius and Kelvin have the exact same size gradation. A Celsius degree is about 1.8 times greater than a Fahrenheit degree. That's going to be very important. Okay, that's just a hint. So make sure that you understand you don't have to necessarily convert between Celsius and Fahrenheit, but just understand that there are 1.8 Fahrenheit degrees in a Celsius degree. So I think that's very important. I think that's worth mentioning. Okay, there are three kinds of energy transfer. There is conduction, when I touch an object. There is convection, which uses the change in density, the thermal expansion, when something gets warmer, when it will rise, so changes in density as a result of the warming of a fluid. I can transfer energy that way, or I can transfer energy through direct radiation. For instance, the sun is not hot, it's bright. So the light, the electromagnetic radiation, passes through the atmosphere very nicely. It has short waves, relatively speaking, and then it's warmed by it's absorbed by terrestrial things like dirt, buildings, whatever. And then it's re-radiated as infrared energy, which has longer wavelengths. And it's the longer wavelengths that have a hard time getting out of the Earth's atmosphere and bounce back. And we call that the greenhouse effect, which is also very important. Don't forget Newton's law of cooling. Very important point. Don't forget about specific heat capacity. The specific heat capacity of a substance is the amount of energy it takes to raise the temperature of 1 gram of substance 1 degree Celsius. If I want to find out how much energy, for instance, was absorbed by water that went from, say, 20 degrees to 30 degrees, I would say it would be the mass of the water times the temperature change times the specific heat of the water equals the amount of energy gained or lost. So you'll need to be able to do very simple problems where you have temperature, change in temperature, times mass, times specific heat capacity will determine the amount of energy that was either gained or lost. Don't forget how the sun warms the earth. I think I've already gone over that. Don't forget about phase change. Evaporation is a cooling process. Condensation is a warming process. Remember the concepts of thermodynamics. It's always a system and then the surroundings. So when energy flows, it travels from high temperature to low temperature. But if it doesn't flow from high energy necessarily to low energy. If I have the ocean contains a lot of energy. Yet, if I put my hand in the ocean, the energy will flow from my hand to the ocean. Because even though there's more energy in the ocean, the temperature of the ocean is less. So in thermodynamics, we say that energy flows from high temperature to low temperature. But please understand the nature of what cold and hot really mean. Energy flows from hot to cold, not the other way around. So understand phase change. So let's say I have water at negative 20 degrees Celsius. As I warm that ice, it's going to gain kinetic energy. As I put energy in there, the kinetic energy will increase. And then at 0 degrees Celsius solid, the kinetic energy increase will cease, and I will get a phase change. A phase change is when I put the energy in, but there's no change in kinetic energy. The entire change is going into an increase in potential energy. So a phase change is when you have a change in potential energy, not kinetic energy. And then when the phase change is complete, so the solid becomes a liquid completely, then the kinetic energy will start to increase again, and I get an increase in temperature. And understand what temperature is. Understand the relationship between kinetic energy and temperature. Some of you had a little bit of a hard time with that last time. And don't forget, when you're heating that water at negative 20 degrees Celsius, and then you get that first phase change, that's called the heat of fusion. So it's absorbing the heat of fusion, which is 80 joules per gram, and then it goes through the liquid phase of water, and then it gets to 100 degrees Celsius, and you get another phase change, where it's approximately 540 calories per gram, as opposed to heat of fusion, which is 80 calories per gram. I apologize. So heat of fusion is 80 calories per gram, and the heat of vaporization is 540 calories per gram. And you could do a joules conversion where 4.18 joules per every calorie. So 1 calorie equals 4.18 joules. So you can do a conversion between the two to know what is the heat of fusion and heat of vaporization in joules as opposed to calories. That is a hint. So anyway, you have two phase changes. One where it's absorbing, going from solid to liquid, the heat of fusion, and the other one is going from a liquid to a gas, where it's absorbing the heat of vaporization. Let's look at one of the single most difficult aspects, I think, of the second semester, and that is the concept of the heat engine. So you may want to make a picture on your notes, the heat engine schematic, where you have high temperature reservoir, low temperature reservoir, and then some of the heat is being used to do work. You might want to draw that down and understand that the greater the difference in temperature between the high and low reservoir, the more efficient is the engine. So let's look at a few scenarios which may help you understand this element of thermodynamics. All right, first scenario. What happens and what accounts for an increase in temperature of a gas that is kept at a constant volume? Remember, it's a constant volume. Well, the only answer would be that the energy must have been added to the gas as heat if it's being kept at a constant volume. Okay, let's look at the heat engine in and by itself. Let's say the heat engine takes in energy as heat and used a portion of it to do work. Now look at your schematic. What must happen next for the engine to complete the cycle and return to its initial conditions? Well, look at your schematic. It's obvious that if you have the schematic drawn correctly, that it must give up the energy as heat to a lower temperature, the low temperature reservoir, so work can be done on it. Okay, let's continue with the problems that we're going to be looking at. Let's talk about entropy. Remember, entropy means disorder, but what's the relationship between entropy and the energy available to do work? So, for instance, if I have a system where disorder is increased, what does that do to the energy available to do work? It would be less. So as the system's disorder is increased, that will make less energy available to do work. So let's say, for instance, I have a thermodynamic process occurring and the entropy of the system is decreasing. What can be concluded about the entropy change now of the environment, of the surroundings? What can be said about the change to the surroundings? And that will be that the entropy in the surroundings will increase. It decreased in the system, but if that's true, it will increase in the surroundings or to the environment. Okay, let's start talking a little bit about vibrations, waves, and sounds. Now, you have to know a little bit about, even though we didn't spend a lot of time on it, and if you remind me, I'll go over it a little bit, but you have to know about just simple harmonic motion, like a pendulum swinging back and forth, and the relationship between the length of the pendulum and the period. So I think that's significant. So if I triple the period, the length of the pendulum will increase 9 times, for instance. So you have to know what a pulse wave is. So if I set a rope against a fixed point, remember the slinky? And someone was holding one end of the slinky and I was putting energy into it. I got that was like a pulse wave. I would send the pulse wave down and it would come back reversed. So it would go along the top and then it would reflect and come along the bottom. Okay? So you got to know what a pulse wave is. What else? You have to know how to convert between a mechanical wave with compressions and rarefactions and a sinusoidal wave. For instance, the compression would be mapped to the crest and the rarefaction would be mapped to the trough. And remember, the distance between the trough and the crest is 2 times the amplitude. So if you think of a XY axis where the sinusoidal curve is going peak to trough along the x-axis, the nodes are along the x-axis, but the amplitude is the distance between the x-axis and the crest, or between the x-axis and the trough. You have to know what frequency is, wavelength. Remember, the speed of sound equals the frequency times the wavelength. The speed of light, same, equals the wavelength times the frequency, same thing. Okay, so let's talk about superpositioning. You're going to have superpositioning. Things are going to be either constructive interference or destructive interference. So it's either going to be noise canceling headphones. That's going to be destructive superpositioning, where I'm going to line up trough and crest, trough of one wave with crest of the other wave. And I'm going to try and, let's say I have these headphones and I'm listening to music and some kind of noise is coming in. Well, the headphones are going to produce the exact same frequency, but it's going to line up its manufactured sound based on the noise so that the superpositioning is crest to trough, so that you get total cancellation or total destructive interference, as opposed to resonance, where you have I put energy in. I keep putting energy into a substance or something like my sinuses, and I hit the natural frequency. Okay, and I put more and more energy in. As I put more and more energy in, I'm going to produce the same exact wave, and those waves are going to line up crest to crest. So that kind of superpositioning is going to result in constructive interference. Constructive interference. So resonation, when I resonate, I'm going to be exciting a substance at its natural frequency, and as that natural frequency occurs, I'm going to create more and more waves, and those waves will add constructively. Let's talk a little bit about the calculations. So if I have a wave that has a wavelength of 3 and it has a frequency of 10, it would have a speed of 30, because it's wavelength times frequency. If I know my speed of the wave is 100 and my wavelength is 2, my frequency would be 50. So it's simply nothing more than the speed of the wave equals the wavelength times the frequency. Okay, you want to look up the relationship between the length of a rope and standing waves. Like, let's say I have a 2-meter rope, right? What's the relationship between the wavelength that would not produce a standing wave and the rope? Another one is, if I have a 3-meter rope, let's say, and I attach it at both ends, if the standing waves with a wavelength of 2/3 L are produced on the string, how many nodes will be formed? Okay, for instance, what is the fewest number of nodes a standing wave can have, for instance? That would be 2. Sound waves are longitudinal waves. Light waves are transverse waves. Now, I can convert between a mechanical wave and a transverse wave, but a sound wave is mechanical and it is not transverse. But I can convert for my amusement between longitudinal and transverse waves. I can map one or the other. know what the trough is, the crest is, the pitch is the frequency, the note is the note of the pitch, know what the timbre is. If I have two instruments that play the same note, but they don't really sound the same, but that's the timbre. The distance between wave fronts of plane waves correspond to what? If I have the distance between wave fronts, what's that? That's simply the wavelength, right? Like the distance between crests. Okay, know what intensity is. The intensity of sound or light will decrease as an inverse square function. Know what, let's see, know what the natural frequency is, know what the relationship is between natural frequency and resonance. Know what beats are, pretty easy to calculate. The difference in the frequency would be the number of beats. The speed of light c equals the product of wavelength and frequency, just like with sound. And you have to be able to calculate between the two. Nothing major. You need to understand that the speed of wave, the speed of light, is 3 times 10 to the 8th meters per second, and that's in a vacuum. That's all light, radio waves. The different types of electromagnetic radiation going from long waves to short waves are radio, micro, infrared, visible, UV, X-rays, gamma, and those are with decreasing wavelength and increasing frequency. Okay, next you have the intensity of light will decrease, like sound does, as an inverse square function. You have to know the colors of light. You have to know what the primary colors of light are, what the primary colors of pigments are, how pigments subtract when they're combined, and how light will add when they're combined. So it's very similar. I'm not worried with your knowledge of 27 and 28 with light and color. Now let's talk about nuclear physics, and then we're finished. So you have electrons, protons, and neutrons. Electrons orbit the nucleus. Protons and neutrons are in the nucleus. Anything in the nucleus are called nucleons. A neutron is essentially a proton with an electron embedded in it. The mass of an electron is negligible, where the mass of a proton is 1. The charge of a proton is +1. The charge of the electron is equal and opposite, -1. Even though it has almost no mass, it still has a charge equal and opposite to a proton. So if I have a proton with an electron embedded in it, its absolute charge is 0. That's why it's called a neutron. A neutron is in the nucleus, and it's a combination of protons with an electron embedded in it. You have to know what a beta particle is. A beta particle is a high-energy electron coming from the nucleus. When a neutron breaks down, it becomes a proton and an electron, and that electron escapes the nucleus. It's called a beta particle. Remember the superscripts and the subscripts. The superscript, let's say uranium, 235. It'll have a superscript of 235. That's a mass number. That's the protons and neutrons. It'll have an atomic number, which is 92. Now, the subscript is actually a charge, although it's never really put in, unless you're talking about an electron. An electron has a mass number of 0. That's the superscript, and an atomic number of -1. So the superscript would be 0, and the subscript would be -1 for an electron. For a neutron, it would be 1 would be the superscript, and 0 would be the subscript. For a proton, it would be 1 would be the superscript, and a +1 would be the subscript. For an alpha particle, you'd have 4 as the superscript and 2 as the subscript. You have 3 types of hydrogen, 3 hydrogen isotopes. You have protium, deuterium, and tritium. Protium, deuterium, and tritium all have 1 proton, so all of their subscripts would be 1, but protium has 0 neutrons, deuterium has 1 neutron, and tritium has 2 neutrons. When I break down, for instance, radon 220, that's the mass number, with an atomic number of 86, when it loses a alpha particle, it becomes polonium 216, and that has 84 protons. So, radon, superscript 220, subscript 86, loses an alpha particle. So, polonium would have a superscript of 216, that's 220 minus 4 is 216, and it would have a subscript of 84, that's 86 minus 2 is 84. When something undergoes alpha decay, it loses a mass number of 4 and an atomic number of 2. When something undergoes beta decay, the mass number does not change and the atomic number increases by 1 because you're increasing the number of protons by 1. But the mass isn't changing because the neutron was converted to a proton, so it's all the same. The mass of a proton and the mass of a neutron are both 1. So a beta decay, the mass number does not change, but the atomic number increases by 1. You have to know that the natural log of 2 divided by the half-life of a radioactive substance is equal to the decay constant. Now, if I have something, let's say a half-life, let's say 3 half-lives. So it would be, at the end of 1 half-life, I'd have 50% left. At the end of 2 half-lives, I'd have 25% left. And after 3 half-lives, I'd have 12.5% left. And after 4 half-lives, I would have 6.25% left. And it keeps going down and down and down and down and down. Okay? Now, also, don't forget that the daughter cells, if I have fission, and fission of uranium-235, and it goes to, so the superscript is 235, and the subscript is 92, that's uranium-235, and its daughter cells would be barium-140 and krypton-93. So barium has an atomic number of 56, so the subscript is 56, the superscript is 140. Krypton has a subscript of 36 and a superscript of 93. So the 2 daughter cells in the fission of uranium-235 would be barium-140 and krypton-93. And that brings an end to our review. Also, don't forget the gamma rays. Gamma rays are a particle, and it has a superscript of 0 and a subscript of 0. Okay? Have a good day. Thank you for listening. Good luck on your final. Don't forget your sheets are due, your review sheets are due on Friday, June 4th. That is non-negotiable. Have a good day and goodbye.